Okay, welcome everybody. Let me just bring up the slides here. And actually, there was one last thing we were going to do before that we didn't quite get to last tutorial. So I'm going to remember last tutorial we looked at STL vectors and saw that they were
Ron, did
yeah
you start the recording? Okay,
yeah I did. We looked at STL vectors and saw that in many ways they were really a better array. They they knew their own size. You can turn on extra checking with the debug check build, so they looked pretty good. So let me just I'm going to change my view here so the recording comes out better. All right, and let me do that here too. Okay, so let me ask you a quick question with the poll.
I'm not sure if you are sharing one.
I'm not sharing yet actually because I don't have any slides up.
Okay.
Okay, so two questions via polls, which hopefully you can see now. So the first time is anytime we talk about speed. So I want to talk about so basically the STL vector is better than an array in terms of its usability. It can grow, it can tell you its size, we can turn extra checking on for it. All good. So the question is, does it cost us any speed? Do we have to worry about this? Before we start talking about speed of code, we need to talk about compiler optimizations. So you have not used this, I believe, in any of your prior courses, but a compiler can be run in what's called a debug mode, where it just translates your program into the machine instructions that an actual processor can execute in essentially the simplest way possible, the most direct way possible. So that's called a debug build. And it's easier to understand if you run through a debugger, it's easier to understand what's going on because your code's been translated in a pretty straightforward way to the machine instructions. But compilers can also do what's called optimization, and that's normally called a release build. And you can do either of these in this course, a release build or a debug build. And in a release build, the compiler tries to generate smarter machine code that is faster. So it might do things in a different order than you specified. You can't tell the difference. It'll get the right answer. But if you ran into a debugger, it's harder to understand because you might see lines executing out of order, but it is faster. So the question is, how much faster is it? That's the first polling question. Does this not matter much if you turn on these optimizations? Does it make it 2 to 4 times faster, 8 to 10 times faster, 100 times faster? How much do you get by turning on this release mode with these compiler optimizations? Okay, and then the second question, so this is relevant because anytime we talk about is this code faster than that code, if compiler optimizations matter to speed, then we want to make sure we're running with optimizations. So we want to make sure we're running with release build. Second question, how fast is standard vector compared to arrays? And I'm asking this with compiler optimizations on because that's what we care about when we're trying to find speed. Are they about the same? Is vector 2 times slower? And I think there's one more option here. Or 2 times faster. Okay, so I'll give you another couple seconds to think about that. Now that I've set up the question, then I'm going to end the polling. Okay, so 5, if you want to change your option, do it now. 5, 4, 3, 2, and 1. All right, so we end the polling, and I'm going to share the results with you. Okay, so 6% of people think that compiler optimizations don't do very much, and then about 44% think it's 2 to 4 times faster is how much the program will speed up. 37% think 8 to 10 times faster, and more than 10% 100 times faster. Okay, so remember those numbers. And then how fast is standard vector versus arrays? So pretty even split. About a third of the class thinks it'll be about the same. A third thinks it'll be slower, and a third thinks it'll be faster. Okay, so that one is a hard one to guess. So let me stop sharing this, and I'm going to go off and we're going to do a quick demo of this. So we're going to take a look at what the computer tells us. Okay, so let me share my screen here and bring up the VNC session. Okay, can everybody see that? It's a bit small. Let me make it bigger. Let me do this too. Okay, how's that look? Hopefully that is legible. Abid, can you see that?
Yes.
Okay, let me remember which one of these I'm... Sorry, I've got two computers open. I have to remember always which one I'm typing on. Okay, so I'm in a directory here with a little sample program. And it's got a program in it. Let's see. Okay, vector versus arrays. All right, so this is the program that I'm going to time. So what does it do? It creates a couple of
Sorry,
arrays.
Gon, this is not the one.
This is not the one.
Yeah.
Oh, yeah, it's not the
You
one.
need to go into the directory,
Yeah, so sorry.
the
No
demos.
wonder I had so much trouble finding it. Thanks, Abbott.
No
Let's see.
problem.
Whoops. Okay.
No, go into the directory demos, and it should be.
Sorry, I'm in the wrong spot. Thank you.
No problem.
Okay, this is the one I want to show you. Okay, so what does it do? It creates a vector, and this constructor is going to initialize that vector to have, let's see, what is that? I think that's 10 million elements, so quite a few, and they're all going to be equal to 20. And then it's just going to go through and it's going to 50 times go through that whole vector and just modify the entries. Okay, so it doesn't do anything super interesting, but it's going to go through this whole vector 50 times, changing every single entry. Okay, so what we're going to do is we're going to compile that and we're going to test. So I'm going to do a make clean because I don't know what the last version of this compile was. So I got rid of my old build. I'm going to do a make, and by default, make just builds the debug build. Okay, no optimization. Turn that C++ code into machine code that can run in the most obvious way possible, which is the easiest code to understand when you run it in a debugger. So that's what you usually debug. And now I can time it using the Unix time command. So there's a command in Linux called time, and it just tells you how much CPU time something took. So you say time, and then whatever the normal command would be. Okay, and this command is vec versus array speed. That's the program I just created. And let me actually show you the program so you can see it while we're doing this. Okay. There we go. I was in the right spot in that one. Okay, so let me bring up the program again. All right, so you can see the code there. It's not super interesting. We're going to time it. We're going to see how long it takes. Prints a little bit of output out. The key number here is this one, the one that comes before the U. That means user time. User time is basically how much time your program took, not including any work the operating system did for you. It's almost the same. So it's almost 1.6 seconds. This number, which is the total time, is 1.6 seconds. So it adds a tiny bit of operating system time in. I could use either of these. I'll just use the first one. Okay, so about 1.6 seconds. So that's how long that took. Okay, now I'm going to get rid of that, and I'm going to build it again. And we have a configuration called release. So this turns on compiler optimizations. And now I'm just going to run that time command again. Okay, so I say bang time, that means run the last command that starts with time. So it's going to do that again. Okay, it took 0.47 seconds, so almost 4 times as fast, maybe 3.5 times as fast. So everybody who said it was between 2 and 4 times faster, that's about the right ballpark. In this case, it was close to 4x. So what does this mean? It means when you're we have CPU time tests in this course. When you're trying to pass those CPU time tests, you absolutely want to be running the release build. When you're trying to debug, you want to run the debug build. So you're going to use both of those. And sometimes you'll run the debug check build when you want even more checking. Okay, so let's take a look at this program. So it's using vectors right now. I'm going to change it to so I'm going to comment out the vector declaration, and I'm going to uncomment the C-style array declaration. Don't change any of the code other than that. So all I've done is go from a vector back to a C-style array. Okay, I don't want to quit, so we'll just save that. Okay, so I saved that. I'm going to compile this again. I'm going to compile it in release mode again because I want to, whenever I'm comparing CPU time, I also want to do it on release mode because I want optimizations on. Otherwise, I might get misleading results. Okay, so I run this again. How long does it take? 0.447 seconds. Okay, so basically both of these are about 0.45 seconds. The array and the vector are extremely close in speed. You can't really tell them apart. Okay? So those who said that vector and arrays are about the same speed, you're right. And if I actually ran this in debug mode, I could have gotten a misleading answer. A vector actually requires compiler optimization more than a raw array. So always do your CPU time comparisons in release mode. There's no downside to using a vector, just as fast as an array, easier to use, has more features, easier to debug. So you should do that. Okay. Let's see. Any questions on that demo, or is that all pretty clear? Okay, I'm going to shrink this back down, and we'll go on to slides. So that was kind of covering something from last week, but it's pretty important to understand how to.
There are some questions on the chat.
Okay, sounds good. Can we build using release mode in NetBeans? Yes. Basically, NetBeans has different configurations that you can select from a GUI, like a drop-down menu, and it's discussed in the Milestone 0 handout. It does exactly the same thing. NetBeans, when you build, is just calling the makefile. Depending on which configuration you have active, it will call it'll pass the appropriate option to the makefile. So it's exactly the same. Why did we use arrays in the first place? Basically, they're lower level and older. So the language, C language, and therefore C++ language have arrays built in. Vectors layer on top of arrays. So as you saw last week, there's an array essentially buried inside of a vector. So it's important the language has arrays, but there really isn't a great reason to use arrays anymore because vectors provide a easier to use object that's higher level and has no efficiency cost in terms of speed. So there are very few reasons to use what are called raw arrays or C-style arrays anymore. They tend to make your code harder to debug and harder to write. So vectors are kind of higher level and better because they don't cost you time. What does the first number represent? U means user time. User time means the time that your code, so the time that your code took, rather than any time the operating system needed to start your program, end your program, do I/O, etc. For all the programs you're going to write, the U time is going to be almost all your time. There's another number after that is the total time. So there's basically U is the time your program took, S is the time the system took or the operating system, and then after that there'll be a total of the two. For all the programs you're writing, you're going to find in this course, you're going to find that user time is almost the same as total time. Okay. And okay, I think that's all the questions. So with that, let's move on. We've got lots to talk about today. Okay, last tutorial we talked about C++ templates. So we had function templates and we had class templates. We went over the pair one. And we talked a bit about the standard template library, particularly standard vector, which is a pretty, as we just discussed, a very useful and important class. Today we're going to talk about some more components of STL. And we're going to talk about iterators first. And I'll describe what those are. Then, and what you can do with them. And then we need these concept of iterators to work with some other what are called container classes within the standard template library. And one of those container classes is a linked list called standard list. And we're going to look at how do we use that and how is it different from a vector. Okay, so what is an iterator? So an iterator identifies an element in a container. So it is similar to a pointer. It's a class, so you don't know exactly how it's implemented. It often is implemented as a pointer with some extra functions, but it might not be. It is sometimes more than just a pointer. It doesn't matter. It behaves like a pointer. So you can use a lot of the syntax that you learned in 244 for pointers with iterators, and it all does what you would expect. So it allows us to access an element in a container. So that's like a pointer. It allows us to move between elements in a container, which is similar to something called pointer arithmetic. You may not have used this in 244, but you can actually increment pointers and decrement pointers. And basically it's moving you from the previous element to the next element and vice versa. Iterators in C++ are restricted to efficient operations. So in other words, if a certain, there are different kinds of iterators to work with different containers, like lists and vectors, and you will not be allowed to do something with an iterator that would be extremely inefficient, would be very slow. It'll just won't compile. And that's to do you a favor, to try to prevent you from writing really slow code. I see a question, are the slides posted? Yeah, so they're on Quarkus under tutorial 2. I think I forgot to put the link in from the tutorial, from the list of just all tutorials. But if you go to the module that includes milestone 0, you'll see a page there that has the tutorial. I'll put the other link in after the lecture. Okay, so why do we need iterators? Well, we already have this square bracket operator for vectors that lets us get to any entry in a vector. So we can just use vector of index to access elements. You can do that for vectors. So for vectors, you don't need iterators that much because you have this square bracket operator. But that square bracket operator implies random access. I can get to index 2 and index 20 very quickly. Not all data structures support random access, so lists don't support it. In STL, all containers have iterators defined, and they're all different. So if I want an iterator, so it's like a pointer to an element in a vector, I have to ask for an iterator. That's what that is. But I want the iterator, this : is the scope resolution operator. I want the iterator that goes with standard vector. And we always have to say what kind of standard vector. So it says I want an iterator that goes with a standard vector of integers. I want an iterator that goes with a standard vector of floating point numbers. I want an iterator that goes with a list of integers. So each of those is actually a different type. So I see a question, what does random access mean? So random access means like an array. In an array, you can ask with this square bracket operator, you can say, give me entry 20, just by putting, just by putting the number 20 in here. Or you can ask for entry 2 million. I'm not going to write 2 million, 20,000, just by putting 20,000 in that square bracket operator. So that's random access. I can very quickly get at any entry in an array or a vector with the square bracket operator. Okay, and a list is a linked list. Okay, so STL provides you with a class called list, which we're going to talk about in a few slides, that is a linked list. Okay, so standard vector functions. So we've already talked about how we access vectors. We can use this square bracket operator. We can modify them also with the square bracket operator. We can grow them with push back, and we can ask how big are they with size. So I already know how to do all those things. Today, we're going to learn some new functions that work with vectors, but not only vectors. They work with the other container classes too. So begin, which returns an iterator to the first element, so a pointer to the start of a vector. And end, which returns an iterator that is just past the end of the vector. Okay, and you use that to see when am I beyond the end of the vector. All of these are fast. So every function that I just talked about is order 1, so very fast. And I see another question in the chat. Do linked lists have random access capability? No, so they don't. So, okay, so we're learning about these iterators, and we're going to start learning about them with vectors, because you know vectors the best. So the way we get an iterator, again, like a pointer to the start of a vector, is we have some object. So I've created an object called myVector, so that's the name of my variable. And I say myVector.begin. And that's going to return an iterator that points at the first element. And that first element would be index 0. If I ask for myVector.end, that's going to point 1 past the end. So it points at, actually an invalid entry. There's nothing there. You can't actually go and access that. But it's kind of a flag. Vector.end, myVector.end tells me, oh, I'm at the very end of the vector. I'm, in fact, past the end of the vector. I should stop. Okay? I see some questions in the chat, but I think I'm going to leave those until we have a break because they seem a little,
I'll answer them if you want.
or if maybe Abid can answer them as we're going. But
Yeah.
they're kind of a little different than what I'm talking about, so I'm just going to leave those for the break. So, okay, so the best way to see what you can do with an iterator is just probably with sample code. So what I've got here is I've got a vector of integers. I'm calling it numbers. And this syntax means I'm initializing it. So you put these curly brackets and you can put all the values you want to initialize it to in there. So I've initialized the vector of integers to have 4 elements, 1, 2, 3, 4 in the first 4 indices. And then we're going to try to do some things with it. So we're going to try to make an iterator. Okay, and the syntax to declare this looks a little intimidating, but it's not that bad once you get used to it. So this says, well, I want an iterator, and the iterator that I want is of type vector of integers. So up here, I had a vector of integers, so I want the iterator that goes with that. So I write standard vector of integers, colon, colon, the scope resolution operator says inside that class, there's an iterator. That's what I want. Okay, so that whole long thing there was the type. I'm going to name my variable it for iterator, and I'm going to initialize it by saying I want it to be point at the beginning of this numbers object. So I call numbers.begin. Numbers is a vector. It's got a member function begin. I call it, and what it returns is an iterator, like a pointer, to the beginning of the vector. Okay, so that's the the kind of the setup code. Now I want to try to do a bunch of things with this iterator. I'm going to try setting it to 5. I'm going to try incrementing it. I'm going to try decrementing it. I'm going to try dereferencing it. So I'm trying here to take what is in the iterator and see if I can put that in X. I'm going to check if it is not equal to numbers.end. So that's the numbers vector. Am I at the end of it? I'm going to check, is it less than the numbers.end? Here I'm going to dereference the iterator and I'm going to set that equal to 27. And here I'm going to update the iterator again, saying I want to take the iterator and make it equal to numbers.begin plus 2. All right, so we haven't explained what you can do with iterators in very much detail at all, but we're going to see how good you are at guessing. And let's see if I can find the polls here. There they are. Okay, let's see. All right, so I have to do the polling on this device. Okay, so I'm going to poll you. I've looked at those lines, and I want you to tell me which one of them, all of them are actually valid except one. Okay, so all of those will compile and do something useful, except one of them. So pick the one that you don't think will compile. And remember, an iterator behaves like a pointer. So it doesn't have to be implemented as a pointer, it may be more than that. But the abstraction it presents is all the things you think you should be able to do with a pointer. It behaves like that pointer. But it's a pointer to be used within a certain container. It's not a pointer to the whole address space of the whole computer, which is what C style or C++ raw pointers are. This is a pointer to be used within a container. It doesn't make sense when you try to go between 2 different containers or 2 different vectors, for example. It's to be used to go through one vector. Okay, so I'll give you another few seconds. Think about what makes sense and what doesn't make sense to you. And then I'm going to end the polling and share it. Okay, it looks like we're almost converged. Oh, got a few more people still voting. There's a reasonable amount of code to look through here, so I'll give you a few seconds to decide on your final answer. Abbott, have you voted yet?
I can't, unfortunately. It doesn't give me the option.
I'm fairly sure that you're going to get this one right.
No,
So,
I wanted to skew the result away from the correct.
okay, so let me end the polling and share these results. Okay, so hopefully you can all see that. So let's see. Most people thought the numbers begin worked, and yeah, that works. It sets the. Let me move this over to the side here, and you'll be able to see what each of these lines actually does. Sorry about that. Okay, so okay, so that first line, does it work or not? Yeah, so that first line basically just creates the iterator and points it to the start of the vector. Okay, this next line is the one that the largest number of people, 46% of people, thought didn't work. And you're right. Okay, it doesn't make sense to set an iterator to 5 because it's not now pointing anywhere in any particular container. It's not clear what 5 means. For an actual pointer to the whole address space of a computer, this means address 5. But for an iterator, it doesn't really mean anything. Iterators are used to point at pieces of containers. We don't know what container this is you're trying to use. We don't know what 5 means. So that's the one that won't compile. Everything else will actually compile. And let's see. Okay, the next one is iterator plus plus. So yeah, that actually points to the next element. So this first line here, this line that set it to numbers.begin, your iterator is actually going to be pointing at that. So IT will be pointing at entry one. After we go through iterator plus plus, then IT would actually be pointing at the next element. So that's what incrementing an iterator means. When we go to this line, so let me get rid of some of this. Okay, so we go to line 4, then we're going to decrement the iterator. So it's going to go back here. So iterator points back at 1 again. X equals star IT. So that, again, is just think of what a pointer would do. If you dereference a pointer, you get what it points at. So we would get the integer that this points at, which would be 1. So this would set X equals 1. Okay, is the iterator equal to numbers.end? Numbers.end is basically, this is the end, right? It's past the end of the vector. So this is checking, is the iterator past the end of the vector? And the answer is no. So this would return true, right? The iterator is not equal to numbers.end. Is the iterator less than numbers.end? So that means is it before it? Okay, we haven't gotten to the ends. And for a vector, we can check that. And so this would also come back with true. Star IT equals 27. So that's dereferencing the iterator, which we can do with a pointer, and we can also do with an iterator, and setting that value equal to 27. So it's going to change that 1 to the number 27. Okay, so that's okay. And then IT equals numbers begin plus 2. What do you think the iterator points at? Which number does it point at when you do this? So just type it in the chat if you know. So this is the last line. It will compile. What does it do? Yeah, it's going to point at entry 3. Begin would be pointing at the first element. So if I add 2 to it, it's pointing at the third element. Okay, and I didn't actually type these in. Click on those. But yeah, that's what each of these things does. Okay, so looping through a vector. Let's see, the question is, does case 9 only work because vectors have random access iterators? Yeah, that's a good question. So this last case requires a random access iterator. So only certain containers, this will only work for certain containers. It will work for a vector iterator. It wouldn't work for a linked list iterator. For a linked list iterator, you don't really know how to do this, so it won't compile. And I'm going to show that in a few slides, but not all. Some iterators they're less powerful, and you can only use a subset of these operations. Vector iterators are the most powerful. Okay, so how will we use this to loop through a vector? So you've already learned one way to loop through a vector. So here's my vector. I've set it equal to 4 numbers, same thing as before. And you learned this last week. Okay, let me actually stop sharing these results so I can get those off your screen. Okay, and So we learned a way to print out this vector last week. We can use indices. So we can say for I equals 0, this size t is really just another word for integer is what you can think of. So don't be confused by that. But for I equals 0, I less than the size of the vector. Let's increment I. And for every entry, let's just print out what's in the vector entry, numbers of I. So it looks just like printing an array. And we're using these indices. We can do the same thing using iterators. So we have to make an iterator of the right type. So we want an iterator that goes with vectors. We're going to call it it. We set it equal to the beginning of the vector. And as long as we're not at the end of the vector, that's what that check is, we're going to increment the iterator. And then at every element, we can print out what that iterator points to. So this is going to print exactly the same thing, and it's going to be the same speed as the code I have above using indices. Now, it actually probably doesn't look quite as nice. So for a vector, I would probably write this one. Nothing wrong with either, but stylistically, I probably prefer indices when I have them. Okay. I see a question, what is size t? Shouldn't it be int? Size t is an unsigned int. So I may change this on the slides afterwards because you can just think of this as int. All right. Size t in C++ is another name for unsigned int. And sometimes people use them with containers, but you don't have to. You can just use int. It's fine. Because it is basically the same thing. Okay, so it just says what each of these things do. Okay, so extract the negative values of the vector. So last week we looked at a routine using vectors to take all the negative numbers out of, well, actually we didn't do that yet. So sorry, we basically looked at how we could get an arbitrary list of numbers. We haven't done this one. So we're going to extract all the negatives from a vector of integers. Okay, so we're going to pass in a bunch of integers. Some are positive, some are negative. And what we want to do is we want to take only the negative ones and we want to return them. Okay, so we're going to return a new vector that has only the negative numbers that were in this original integers. We're going to need a temporary variable for that. So we've already given you the declaration. We've declared a vector of negatives. You're going to use iterators to get some familiarity with them, looping over this input integers vector and adding all of the negative entries into this negatives, which will then be returned. Okay, so that is your task. And let's see. So we're going to split you into breakout rooms. And Abbott, I'm not sure I can do this. So I think you may have to do this.
Yeah, I'll do it.
And you know this. Hopefully you've clicked on the URL in the chat. If not, go to the very top of the chat. And this is exercise 1. We'll give you 4 minutes, work in pairs, and just try to write that code. Okay?
So you should have received all an invitation to join a room by now.
Okay, I'm going to join into a room then. We'll see what happens here. You might want to take me out of one of the rooms because I'm going to be going into 2 rooms, so it might be boring for somebody.
Sure.
And if there's a room with only one person, then you can merge them.
Not everyone joined yet, so I'll wait.
I wonder if I should join one or not. I'm scared. Okay, I'm going to pause the recording.
Well, I think you are muted if you want.
Oh, sorry about that. It looks like it brings you back from, I keep forgetting it brings you back from breakout and mutes you. So hopefully you can hear me now. Hopefully that went well for most of you. You're not given a lot of time, so don't worry if you ran out of time. You can just go over it later. If there are any questions about that exercise, please just type them into the chat. And I'm going to make sure that I've got my recordings going again. And it looks like I do. Okay.
You muted yourself.
You're muted again.
Okay, can you hear me now?
Hear you. Yes.
Okay. Sorry about repeatedly muting myself. Okay, so I see at least one person said there was some error with the templates. Yeah, there's a reasonable amount of syntax. So this is where you get into some error messages. You got to read them pretty carefully. And I see someone saying that auto would make this a lot easier to type. And we're going to talk about that in a couple slides. So yeah, there are ways to reduce the amount of syntax. Okay, so what did the code look like? Something like this. You're going to take an iterator and set it equal to the beginning of the container, integers. You're going to loop through as long as you're not at the end, and you're going to increment the iterator each time you go through. You can dereference the iterator to see if what you're pointing at is negative or not. If it is negative, then you push it into the end of that negatives container, and then when we're done, we return negatives. So, okay. What if we wanted to erase the negatives in this original integers? Okay, so we just captured all the negatives, we put them in that negatives vector, but let's say that we add to the spec that we also want to take them out of this passed in integers vector. And it's passed in by reference, which means we can change it. So how do we do that? Well, we're going to loop through the whole vector again. So we know the syntax now from the beginning to the end. We're going to do something. Now, it's a bit weird here. We're not actually incrementing the iterator, and that's on purpose. What we do in the body of the for loop instead is we say if what's pointed to by the iterator is less than 0, so it's negative, we're going to erase it. And there's a member function called erase for vectors. So we say integers.erase. We need to know what we're erasing. We pass in the iterator. So erase the element that I'm pointing at because it's negative. Now I just erased or destroyed that element. So basically my iterator is now pointing at an invalid element. So what am I going to do? Well, erase returns a new iterator. So that's important. We basically capture a new iterator because we just destroyed this one. That's been basically deleted. So it's like an invalid pointer. We need to update our iterator. If the value we're pointing at was not negative, then we're not going to delete it. We're not going to erase it. And in that case, we just skip over it. And we know how to skip over something. We just increment the iterator. Okay, so, and what this iterator points to, good question of what does this iterator point to after the erase function? It points to the next element, because that's usually what you want. Okay, so let's just look at what this erase does. So we have this vector, and as we go through, the iterator is pointing at where we are in the container, in the vector right now. So we've processed everything to the left over here. We have not processed anything to the right, and we're currently pointing at this certain element. If that element is negative, we call the erase function, and we get a new iterator. Okay, so I'll call it IT2 in this case. That's what's returned from erase. What happens is basically this negative is deleted. It's gone, okay, by the erase call. All of the elements after it are basically copied over by one. They're copied down one index so that the vector doesn't have any holes in it, because I just deleted maybe the thing that's at index 23. I need to copy what was at index 24 into index 23. I need to copy what was at index 25 into index 24, and so on. So all this stuff gets copied down. And this new iterator points at the next thing I haven't processed yet. Okay? Does that make sense? Okay. So how fast is this? So this is a new member function, erase, takes something out of a vector. It accepts an iterator to the element that should be erased. Because we're going to destroy that element, we need to update the iterator so it returns the next iterator in the vector. And it's slow. because of this shift, so let me get rid of some of this. This shift is slow. This could be n elements. That's the order n. Computers don't know how to copy all of these elements except one by one. So it's going to copy all these elements over to move them down one index, and that's slow. So it's an order n operation. So given that, what is the complexity of remove negatives? Okay, so let's go back here. Let's look at remove negatives again. Let me erase all this stuff. So erase for a vector is order n because of all this copying to get rid of the empty spot, all this shifting over. So if you look at this code, and you know that this erase is order n, and we could have vectors with all negative numbers. Yeah, so I see people saying, Mark is saying it could be n squared, and that's right. So I can go through this loop n times, all right? And every iteration through, I could have a negative number, so I could do order n work. I multiply those together, and I get an n squared algorithm, which is not great, okay? So let's go look at that. Yeah, so this could be an order n, this will be an order n squared algorithm if we have all negative values. So that sounds kind of bad. Okay, so we've written this function to remove the negatives from a list of integers, but it's going to be slow if that integer list is long. So in order to make it faster, let's look at another container class, and that's where list comes in. So list, standard list, this is in the STL library as well, is a doubly linked list. So you wrote those in 244. So we have a head pointer. It points at the first data element, and each one of these linked list nodes has a next pointer to go forward, and it has a previous pointer to go backwards. And we also have a tail. Okay, so it's a linked list. We can start at the head, we can start at the tail, we can go forward, we can go backwards. Same kind of thing as you wrote in 244. And it's templated, so this data can be anything, right? It could be a linked list of integers. It could be a linked list of float, could be a linked list of some complicated object or structure that you've created. All depends on what the data is, and that's why it's templated. We can store any data we want without ever rewriting this. Okay, so hopefully this is just review from 244. If not, type in the chat. What are lists good for? Lists are good for insert and erase. When we want to insert something in a linked list, if we have an iterator to a certain spot, right here, say I have an iterator pointing at that, I can insert something before that with order one operations. So I can put a new entry in here with some new data, and all I have to do is update this next pointer, and then I'll point this here, and I update this previous pointer, and there's a point there. So I update a few pointers, and I've inserted a new element. And it doesn't matter how long the list is, so it's fast. It's actually an order one operation to insert something at an arbitrary point in a linked list. And it's the same for erase. For erase, hopefully you can see the same thing, that if I had an iterator and I decided that I want to erase this, so if I do iterator and if I call it the erase function on this with a certain iterator, that gets deleted, and I just have to fix up a few pointers. That pointer gets fixed up, that pointer gets fixed up. That's an order one operation because I do the same thing no matter how long the list is. So that's what lists are good for. And this just summarizes that. Okay, so begin and end are always fast for both vectors and lists. Pushback, so growing is fast for both of them. Size is actually fast for both of them. Square bracket operator implies random access. It's fast for a vector and it will not compile for a list. The reason it won't compile for a list is coding it would be kind of bizarre and it would be really slow because a list does not provide random access, so it just will not compile to prevent you from trying to do silly things. Erase, so erase takes an iterator. It's slow for a vector. We just saw that, and I just showed you it's fast for a linked list because we just fixed up a few pointers. Iterator type. So the iterator you get with a vector is called a random access iterator. And the iterator you get with a list is called a bidirectional iterator. A random access iterator is more powerful. It allows more operations. So it allows increment, it allows decrement, and it allows just skipping over an arbitrary number of entries. You can just add 5 or add 20 and so on. And it's because a vector allows random access. You can do this efficiently with a vector because underlying the vector, the key storage is an array, which would allow this to be done efficiently. For a list, you can go forwards, you can go backwards, because those can be done efficiently with a linked list. So with a linked list, you wrote this in 244. But basically, if I have, let's just see how this would work. If I had an iterator here, and I said, sorry, this is kind of messy. Try this again. If I had an iterator pointing at here, and I decremented it, all that happens is I follow the previous pointer, and it goes there. Okay, so this is where iterator would become, right? Maybe I'll draw an arrow there to show that's what happened. That was a very fast operation. And so what the iterator did for a vector versus a linked list, the underlying implementation of how they work can be quite different, but you don't care. I just asked for the iterator to be decremented, and it did the right thing. It went to the previous entry. And for a list, it's fast. However, random access like IT plus 5 would not be efficient with a list, and therefore it is not allowed, just like that square bracket operator is not allowed. If you try to write this with a list iterator, it will not compile to tell you this doesn't make any sense. You shouldn't be trying to do this with a list. Okay? Okay, Iterator Categories. So random access, vector is an example of that. Most powerful iterator has the most operations. Bidirectional, like a list, a little less powerful. Okay? Yeah, so for random access iterator, we can jump around with it. We can increment, we can decrement, we can dereference. Bidirectional can still dereference, can still move forward, can still move backwards. There are even less powerful ones called a forward iterator. So there's another kind of linked list called a forward list, which you probably won't use in this course. What a forward list does is it basically doesn't have the previous pointers. So all these, let me erase this, but basically all these previous pointers, they're not in there. And that means, and actually there's no tail pointer, I don't think either. Basically, for a forward list, you can only start at the beginning and go forward. You cannot go backwards. Why would you ever do that? Well, if you know in your program that you never have to go backwards, you process the data once, you can save some storage by not having these previous pointers. So to allow you to do that, STL has a forward list container. It's only a little bit more efficient in terms of memory than a regular list, so it's not nearly as heavily used. And let's see. And yeah, you can dereference it and you can go forward. You cannot go backwards. So there's a question, what's the purpose of the tail pointer? It allows you to go through the list backwards. So you can start at the end and go backwards through the list. And if you didn't have a tail pointer, you couldn't do that. So for a bidirectional list, it's kind of useful. Okay, so yeah, you have these different categories of iterators and they have different levels of power. Okay, so we just saw that erase is not efficient with a vector. So we had this order n squared algorithm to remove negatives from our vector of integers. And we want to see if we can do better. And we know that list actually is much better for erase because we only fix up a few pointers, it's order 1. So what do we have to change? This is our remove negatives using a vector. We already covered this just a little while ago. Type it in the chat if you've got an idea. What do we have to change this to work with lists? Okay, and not lists that we're going to code ourselves. We're using STL. So we asked for a vector. We just want to use the STL list. What do I have to change? Okay, so change standard vector to standard list. That's a great answer. Okay, and that's exactly right. So it's just that easy. The only thing that's changed between these two pieces of code is the red text. So the vector changed to list. And it works, and it's going to be faster because I got rid of an order n erase and made it order 1. So my overall algorithm is now order n, for the whole loop. So the algorithm is now order n because this was order 1, whereas it used to be order n squared. So STL is smart. It basically, or is well designed, it uses the same member functions, the same operators, regardless of which container you're using. So because of that, I could just change the container I ask for from a vector to a list, and everything else is the same. I still call begin, I still call end, I still can dereference the iterator. So it's quite nice. I can actually change my data structures fairly easily. Is there a way to cast a vector to a list? That's a good question. Is there a conversion operator for a vector to a list? I actually don't know. I don't think STL provides a conversion operator to convert directly from a vector to a list. But I'd have to go and check c++.com to see if that exists. I don't think that conversion operator is written for you. So you could
That would be dangerous. It would lead to a lot of compile errors if you don't know how. Like if you
Sorry,
wrote the
what is that,
code,
Abid?
it can be dangerous if you wrote the code in a way for vectors using a random access and then cast it to a list. The whole thing can change.
Yeah.
So
Well, in that case, but it won't compile if you try to use.
yeah, it
So
won't be it won't be code.
if you use iterators, it's easier to change your code from a vector to something else because iterators are supported for everything, and the random access square bracket operator isn't. On the other hand, there are some things, if you use random access iterators, like if I added 5 or I or something to these iterators, then that wouldn't work. So if I'm using the basic operations for a container, then I can just change from, say, vector to list. If I'm using some operations that only exist for vector because it's more powerful, then it won't compile. I'll have to go look at it. But still, STL makes it not that hard to change from one container to another because of the fact that they do use the same keywords, the same syntax for the same operations. Okay. And that's basically what this slide says. So we just talked about that. And in a minute, we're going to do a demo on this. But before we do that, a couple more things. So we've been typing some pretty long declarations for these iterators. And C++ gives us an option to not type so much called the auto keyword. Okay. So what does auto do? It basically, when the compiler can figure out what the type is itself, you can just use the word auto and it'll just figure out the right thing to do. The type, some students get confused. They think this is kind of like Python where maybe the type can change over time. It can't. This basically is just saving you typing. Where the compiler can figure out, well, the type has to be this, then you can just use the word auto. It'll never change. It's just like you typed in the full type. Okay, so let's just look at the code we wrote. So this is code that basically goes through and prints out all of the values in our numbers vector. And we've used iterators here. And you can see we've got a pretty long declaration for this iterator. Give me the iterator that goes with a vector of integers. We don't have to type that whole thing if we don't want to. We can replace that with auto. Why can we replace it with auto? Because we're immediately taking this object, it, that we created, and we're assigning something to it. And what we're assigning is whatever begin returns when we call it on the object numbers. The object numbers is a vector of integers. Begin is going to return an iterator to it. The compiler can look at this and say, I know what this returns. That returns an iterator. And given what numbers is, it's got to be an iterator to a vector of integers. So it knows exactly what the type has to be. So we can just say auto, and the compiler will fill in the blanks. If we had just tried to, if we didn't have this, if we weren't initializing to something, then we couldn't use auto because the compiler could not possibly figure out what we want if we weren't immediately initializing it. But we are initializing it, so we can use this shorter syntax. Okay. Any questions on any of that, or is it all pretty clear? Okay, so it's all pretty clear. I'm going to try to bring up my VNC viewer again. Hopefully it hasn't shut itself down. All right, we'll see how fast I can find the right directory this time. Okay. Okay, so basically what we're going to do is we're going to do that extract negatives in two different ways. Okay, let's see. Okay, so this is basically my extract negatives function right down here. So what is this code doing? So this code is basically declaring a vector with a lot of entries. It's got let's see, 1 million entries in it. Okay, so I made a vector with 1 million entries. This is going through that vector and basically is putting random numbers in it. Okay, it's putting random numbers in it. That's what this, so we're dereferencing the iterator, sticking random data in it, and half of the numbers are going to be negative. And then we're going to do our remove negatives. And you already saw how we coded this. We're just going to go from the beginning to the end. And whenever it's less than 0, we're going to call the erase function. And you saw we have to capture the iterator that comes back, the pointer to the next element. And if it wasn't less than 0, then we just skip over it. Okay, so same code we had before with just some initialization to make a vector of 1 million elements with random data in it. Okay, now let me show you. This is exactly the same code, except we've changed from vector to list. Otherwise identical. So just changed what container we're using. And this one is called list erase. So two versions of the same code. One uses a vector, one uses a list, and they're both doing a lot of erase. 1 million element container, half of them negative, and we're going to erase all of those so that we get a smaller container at the end. Okay, so let me leave that up. Okay, so I'm going to build this code. Let me get rid of anything that's lying around. So I go make clean to get rid of the old, anything that's been built before. And what configuration should I build? I want to test speed here. That's the whole goal. So I want to compare my vector versus my list implementation. So yeah, I should do this with release. So if I do it with debug, which is the default, well, I can't really trust the results. So I'm going to build this with release. This built me two programs. The first one is called list erase. All right, so it's going to erase. I want to time this. Okay, so I'm going to use my time command. So time, then whatever I want to time, which is this list erase program. I run it. And let's see, how long did it take? So it didn't take very long. So let's read this output. So the user time in seconds, so that's the time my program took, not including any operating system time, was a fraction of a second, 0.045 seconds. So about less than a 20th of a second. If you want to read the rest of this 0.008 with the S, that's system time. So that the operating system needed 8 milliseconds. And when I add those both together, it's still really small. So 5/100ths of a second. That's how you read this whole thing. But basically the first number tells me everything I need. The other two are kind of, well, the last one's just kind of repetitive. So less than a 20th of a second for this program. Let's run the vector one. Okay. How long do you think it's going to take? Okay, so it's n squared. List was n. It's going to take more than a second, I guess, because it's been running for a little while. 1 second, okay. And it gets easier to guess as time goes off. So tree fitty. I'm not sure what tree fitty is. Maybe that's infinity. I'm not sure. Okay. But you can see it makes a big difference. Okay, so it's just finished. And if we look at this output, this took 34.2 seconds of user time, or 34.2 seconds of user time. And again, if you prefer reading this number, go ahead. That includes the operating system, and it's 34 seconds, 21/100ths. Someone asked, what's the 80% mean? It's a good question. I believe that's the fraction of, I'll have to actually go look that up afterwards. I don't actually remember what the percent means. I never pay attention to that. But basically, we went from a 20th of a second to more than 30 seconds. So more than a 600x slowdown. So getting a good data structure that gives you a good computational complexity in your algorithm matters a lot. 600x, so this would be a disastrous choice of data structure. You would fail tons of speed tests. Your program would be really slow if you actually coded this with a vector instead of a list. And you can see to speed it up, we changed one word, right? All we did is we changed this container from being a vector to a list. So it was pretty easy if we know our computational complexity. Okay, and let's see if I can shrink that. And I think that ends that section. So we're going to take a break there. Let's take a break for, we'll start again at 11:20. So let's take a 5-minute break, and then we'll get going again. And I'll be here, and Abid will be here. So just ask any questions that you might have in the chat.
I see. Can you hear me?
Yeah, I can hear you. Okay, so that's an interesting question. Let's go back and look at the code. So, all right, let me erase this. So you're asking, why did we code this loop in this kind of funny way? We set the iterator to the beginning of the list. Well, let's not do the list. Do you want me to do the list code or the vector code, or you don't really care?
It doesn't really matter. I'm just wondering why, like in the third spot of the
Okay, so let's do the list code then. You're right. They're basically the same, so it doesn't really matter. So we set the iterator to point to the beginning of the list. We check it's not equal to the end of the list, and you're right, we don't increment it. So this means don't do anything with the iterator. The reason we don't increment it is there are two cases. If what the iterator is pointing to is less than 0, then we're going to erase that element, delete it. It's gone. Okay, so now our iterator is pointing at an entry that doesn't exist anymore. So we wouldn't want to do anything with that iterator. It's like an invalid pointer. So erase returns a new iterator, and that new iterator will be one past where we were pointing. Points at the next thing, next thing we haven't processed. If it wasn't negative, then we can just iterate, or we can increment as usual. Just skip over it. Okay? So basically it's because we have two cases. Because we're actually using erase, and therefore we're destroying elements, we can't just increment the iterator through this loop every single time. It won't walk through the list or the vector in the right way because we're actually changing the vector or the list. So we need this more complicated code. When we erase something, we need to capture the iterator that comes back and say that's the next thing to process. And if we didn't erase something, then we just say, fine, skip over that one, which is our normal increment. But if we move that increment up here, then it would be done every iteration through the loop. And we can't make it work. In that case, if we captured the iterator, like let's say we just got rid of this else, and we put the IT++ up here, we're going to actually wind up missing some elements now. Because when we erase something, okay, so we erase something there, the iterator now points at the next element, and if we always incremented, instead of processing that element, like checking if it's negative, we'd actually skip over it. So we'd wind up with some things we never processed. Does that make sense?
Yeah, thank you.
Yeah, so it does look a little tricky at first. And it's because of the fact that we're using erase. And erase has this more complicated behavior of what do we need to do with our iterators.
I have a question about the demo.
Hello?
Yeah, so in the demo, you said that the vector and the list is filled with random numbers of, like, they could be negative or positive.
Yeah.
So wouldn't that vary between the two test cases? So one,
they're technically they're pseudo-random. Okay, so pseudo-random means to the human eye they look random. They don't look like there's any real pattern to them. But because we're calling a random number generator that always produces the same sequence of random numbers every time we create it, both sequences in those two programs will be the same.
oh, okay.
So you're right. The technical term for that is actually pseudo-random, because every time you run the program, or in this case, two programs that are both written the same way, they will actually get the same sequence of numbers, but the sequence looks random.
Is there a way to like have a completely random random number generator in C++, or is
Yeah,
that not
there are
possible?
ways to make it completely random. You basically, so a pseudo-random number generator goes through a long sequence of numbers that look random, starting at some point. So it starts at a point that's called the seed, which is like the first number that it returns. If you want a truly random sequence of numbers, the easiest way to do it, there are multiple ways to do it, but the easiest way is make that seed, and there are calls to set that seed, the first number that comes back, make it a function of the time or some other random thing that you can measure. So time tends to be pretty random. If you take time in like nanoseconds, that turns out to be pretty darn random. And that means that every time you run the program, what sequence it starts with will be different, and therefore it always produces a different sequence of numbers. Does that make sense?
Okay. Yeah, thank you.
There was actually a case, this is probably 15 years ago, of a slot machine maker who they had a flaw in their slot machines that they didn't actually hook up the pseudo random number generator that decides whether you win or not to an actual random thing. So every time you restarted the slot machine, it would go through the same sequence. And somebody figured that out and made millions of dollars. They actually, because they actually noticed the pattern, and therefore they could figure out when these slot machines would pay off. And the slot machine manufacturer, I think, had to reimburse the casinos for the fact that their slot machines were not truly random. They were going through a long sequence of numbers, but I guess if you spent a long enough time in the casino, you could figure out that after you unplugged these things, they always went through the same sequence. So you don't do that. Any other questions? Okay, so in that case, let's go on to the next topic. So other containers in the STL. And you're going to use everything you've learned so far. So we're going to build on your knowledge of containers, build on your knowledge of iterators. We're going to talk about other types of containers. So far, you know list and you know vector. There's another class of containers called associative containers. So associative containers, you can look things up by a key, whereas vector and list are called sequential containers because you basically look up things. They're efficient at looking up things by where they are in some sequence. They know if you're the first element, the second element, the 50th element. Whereas these associative containers, they don't really have a notion of what's the 50th element. You look things up by a key instead. Okay, so when would you use those? And we're going to talk about two different types, an ordered associative container and an unordered associative container. Those sound intimidating, but that you already know what both these things are. An ordered associative container is a binary search tree, and an unordered associative container is a hash table. So you studied both these things already in 244. They're both in STL, and you can just ask for them instead of coding them by hand. And there's a question of, is this the same as random access? It's not the same as the random access of a vector, because in a vector you can say, give me what's at index 5, and maybe that's a string called Bob. With an associative container, you can actually say, return to me the data associated with key Bob. So it can be indexed by things that are not integers. And then we'll look at the end at some differences between hash tables, unordered associative containers, and ordered associative containers, which are binary search trees. Okay, and I see actually, okay, this is probably a useful thing for me to know. So you didn't get to hash tables in 244? All right, so the last part of this then may be pretty fast. I will post some slides on what hash tables are, and maybe we'll put that in a future tutorial as well. You don't need to know a lot about how a hash table works in order to use them. So I'll post some slides that I used to teach in 244 on hash tables after this. Okay, but most of this lecture is not about hash tables. Okay, so let's do some motivation. Why do we need these things? So first, how do we find the value how do we find some value in standard vector? Okay, and I don't mean I want what's at index 5. I want to find, for example, let's say I have a vector, and in it I put a bunch of strings. Okay, so there's mu, ba, la, ti, da, and I want to go look for la. I want to see if that's in there, and I want to get an iterator to it so that I can change it, look at it, something. Okay, I can do that without much code. There in STL, there are a bunch of algorithms They're basically templated functions. One of them is called find. So I can call this function find, and it takes two iterators, a start of where you want to start searching in a container and an end. So I just say I want to search an entire container called myvec. So I want to search from beginning to the end, and I want to look for the value law. Does it exist? And it turns out that it does exist. It's right there. So I get an iterator that points at it. Okay, so it's not much code at all, right? I could do this myself with a for loop. So you now know how to use iterators, you know how to do reference. So you could write this yourself with a for loop. This is even more convenient, right? I call one templated function and I can find this thing in a vector. But it's order n complexity, because the way this function works for a vector is exactly the way you would write it. It's a for loop. It basically checks, it starts an iterator here at begin. It says, is what that points to equal to law? It isn't. So it moves the iterator to the next thing by incrementing it. Says, is that equal to law? No. Moves to the next element in the vector by iterating or incrementing the iterator, checks it, finally finds it. That is an order n operation, because it basically has to look through the whole list to see, is this data value in there or not? So easy to code, but not very efficient. Yeah, as a question, if law wasn't found, does it return myvec.end? And yes, that's exactly what it returns. So this is like a null pointer. It means invalid iterator. You return that, it means I didn't find it. And that's the STL convention basically all the time for I didn't find something, invalid iterator, it like returns end. Okay, so that's one option. Now you could say, well, okay, if I need to do rapid lookups in this vector of strings, then I could sort it. I could store it in alphabetical order, and I could write some binary search routine. You learned how to do this, I think, in 244. If you basically start in the middle, and depending on whether you're less than or greater than the string there, you know, you'll go look in the left half or the right half of the vector and so on. So you could write that. You could write that binary search routine. You could keep the vector sorted. But it's a lot of extra code, and it's actually error prone, because you need to make sure the vector is always sorted. So if you go insert something new in the vector with pushback, you got to go and resort the vector. So it's going to be a pain. So instead, we can and should, if we need to do a lot of accesses like this, if our code is doing this very often, then basically vector is not a good choice. We've chosen a container where our fundamental operation of finding things by the what we've stored, not by index, but by what we've stored, is not efficient. So what data structure should we use instead? So it's inherently ordered. You studied it in 244. What should we use? Type it in the chat if you know it. Yeah, binary search tree. So that's exactly what we're going to use. So thank you. So we're going to use a binary search tree instead. It's much faster. In STL, that is called a map. So it just means binary search tree. Okay, how does it work? It's a self-balancing binary search tree. So in what self-balancing means, so in 244, you found that if a binary search tree is balanced, meaning it has the minimum number of levels, then it's very efficient. Finding things, inserting things, erasing things are all order log n if you have a balanced binary tree. But if your binary tree became unbalanced, if basically it was constructed so there was only, say, one child, a right child of everything, then it becomes much less efficient. In the worst case, it can become order n, just like a linked list. The binary search tree inside of STL is self-balancing, meaning as you do inserts and erases, it will restructure the binary search tree if it has to, so that it keeps it balanced. So it's always going to be of this form on the left, and it's going to guarantee that it's log n access. Okay, how do we interact with the binary search tree? It uses standard pair. So it actually uses the templated class that we wrote last class. Well, it uses the standard library version of that. The first element in the pair is the key. So what you're going to search for when you're trying to find things. And the second value in the pair is the value. So like the payload, the data that's coming along for the ride. Okay, so to give you an example of this, and I don't think you got to this in 244. So this is one of the labs that I used to teach in 244, but I don't think you got there. Tell me if I'm wrong and you did get to it. An example of using this would be a domain name lookup. So on the internet, you type in nice names in your web browser, like, or in putTTY like this, ug152.eecg.utoronto.ca. So a nice, easy to remember name. That's not actually how the internet works. It doesn't send packets based on names like this. It sends packets to addresses. Those addresses are 32-bit integers that identify computers around the world. So they're actually a 32-bit integer. So this actually is the integer that goes with this computer. So that really is the IP address of this computer. I looked it up before class. And you're probably used to that being shown 1 byte at a time. So it's usually not shown as a 32-bit integer. For printing out to humans, it's written as 4 1-byte numbers, but it's actually stored as a 32-bit integer. There are what are called domain name servers scattered around the planet that translate between these names that a person would type in and these integers, which can actually be used to connect packets to various computers. And they have to be fast. So these domain name servers, you can imagine there are a lot of names of different computers and different domains and networks and so on. So they have a lot of strings and they have to rapidly return a lot of different integers. So they wouldn't want to store all of these names of different computers in the internet in a vector and just search through the whole vector, seeing which one matches. So they don't do that. They use a more logical thing would be to use a map, a binary search tree. And for this particular example, that binary search tree would have a key, which is the string, because this is what we want to be able to find things by. I want to type that name in, and the value, the payload, I want to get this integer. I want to know what my networking software should actually connect to. So the key should be a string, and the value, the payload, should be an integer. Okay? Okay, so that's the motivating example. How do we write this? Okay, so we need to include a new header file, map, and here's my main program. First thing I do is I say I want to create a binary search tree. So we say I want a map, a binary search tree, and I need to give it 2 data types because I need to say what kind of binary search tree. So I want my key to be a string and I want my value to be an integer. So I say both those things in this template declaration. And then this is just the name of my variable. So it's a regular variable, but it's a binary search tree with string key and integer value. Okay. And this actually says all these things. Let me erase my notes. And then I'm going to put some stuff into this binary search tree because it starts out empty. And I'm going to show you 3 different syntaxes for that. They all do the same thing. You can just figure out whether you like it to be more explicit or more short. So this first syntax, I want to put google.com, that string, and this IP address. That's the identifier for where its packets should go. So I'm going to make a variable called Google, and that variable is of type pair, and it's a pair of string and integer. And I'm going to construct that data element or this object right away with a string and an integer. Okay, so that's the first way I could do this. I make an explicit variable called Google of the right type, and then I just call on my binary search tree, I call its member function insert. So insert is the opposite of erase. Just put something into this binary search tree, and it'll put it in the right place. The binary search tree is kept, ordered and balanced. It'll handle all of that. Okay, so that was my first option. My second option does the same thing, but now it's Apple and a different IP address. And I'm going to make it a little more succinct. There's a function called makePair. It's a templated function that STL provides. So for any pair of data elements, so a string and an int, it just makes me a pair of the right type. So it'll make me a pair of a string and an int. And I'm going to assign that to a variable, Apple. And I can say that that's an auto. Okay. Because of the way I've written this, the compiler can figure out, okay, you just made a pair of a string and an integer. So that means I know what auto should be. Auto must be a pair of type string and integer. So it's a bit shorter, and then I insert that into my binary search tree. And then the third one is I just get rid of the temporary variable apple. I didn't really need that temporary variable, so if I want, I can just directly take this, and I can directly insert it into the binary search tree. So in this case, I'm making an unnamed object with utoronto.ca and a certain IP address, and I'm directly putting that in with no temporary variable. And it just saves me some typing. All three of these do the same thing, so use any one of them you want. So there's a question. So make pair can figure out the types of the string and the int? Yeah, make pair figures out what the types are, and it makes a pair of the right type, and that's why we can use the auto here too. So do we need to include any other header files to use standard make pair? That's a good question. So I believe this actually compiles without any other header files. If you had any problem, then you'd basically go do a search at a website like c++reference.com to see where is make pair. But I think make pair gets implicitly included by map, and that's why it works. Which option would be most efficient? They're all going to be the same. So when you turn on compiler optimizations, the compiler is going to figure out how to make the most efficient code. And basically all three of these things are doing the same thing. They just, one of them is shorter than the others. It's going to be the same speed. So you can do whatever you find easiest. Okay, that just documents what each of those are. Okay, so searching standard map. So the whole point of binary search trees is really to make our find function fast. We want fast finds by a key. And so here, I'm just using the short syntax. So I've inserted my three values inside of my binary search tree. So that's basically what I did on the prior slide, but using the short syntax. And now I want to go look for a couple of things. And the way we look for things is we say binary search tree, call the find member function, and it's going to return an iterator. So if it finds it, it's going to return an iterator that points at that element in the binary search tree. If it doesn't find it, it's going to return the end iterator, like this invalid iterator. So question I want to ask though is to see if you're following along on this. What do you think we should use in the input to this find function? Okay. So should we, let's say I want to go look for utoronto.ca. Okay, so utoronto.ca had, this is the key, right? The name, this is the value, the IP address. And what should I use? What should I pass into that find? So let me do a quick poll here. Let's see, so launch the polling. Okay, so I'll give you a few seconds. Should I pass in the key to find? Should I pass in the value to find? Or should I pass both in to find? So we haven't really taught you how this works yet, but it is a binary search tree. So think of what you would do with a binary search tree and what makes sense. What are we trying to achieve with a binary search tree? Okay, so just give you a few more seconds. So if you're thinking about it, you got a few more seconds to take a guess. I'm gonna close the polling in about another 5 seconds. So 4, 3, 2, 1. All right, so let's share the results. Okay, so about 60% of you thought we should pass in the key, and the key would be, this string. About 27% thought we should pass in the value, which would be this, the IP address. And about 14% thought we should pass in both. And yeah, the right answer is key. So the point of a binary search tree is we want to be able to look up quickly by key, in this case, these strings. And once we have the iterator, then we can get the value. We can get whatever the payload data is. Generally, we can't pass in both the key and the value because after we're usually searching, like a person typed in www.utoronto.ca, or that's come from a program trying to connect to utoronto.ca, and that program is asking what is the IP address. So it only knows the key, and it is saying I need to get this iterator so I can go find the value. So key is the right answer. Okay, so in this case, we look by things like apple.com and maybe microsoft.com. So how do we check if the key was found? I basically already told you this, but we'll see if anybody remembers. So type it in the chat. How can I tell? It returns an iterator. How can I tell whether it was found or not? So what's the special value that would tell us it wasn't found? Okay, so second thing in the pair. Yeah, it's basically if it's not equal to the end iterator. So that's exactly right. So the special value is the end iterator. Think of end iterator kind of, well, it's one past the end of the container. And in cases like this, you can kind of think of it like a null pointer, invalid iterator, special value. So if the iterator is not equal to this end value, it means we found it. Okay, the iterator is pointing to a pair. That's what we put into this binary search tree. So we can actually ask for the first element in the pair, which is going to be the key. And we can ask for the second element in the pair, which is the value. And are you guys familiar with this notation, this arrow notation? Do you recognize that from 244? Yeah, so that basically means if I have a pointer to a structure, I can use this arrow notation to say, get me this member within the structure using that pointer. Iterators, because they behave like pointers, they present that abstraction, you can use the exact same syntax with them. Okay, and down here, in this case, there is no Microsoft.com that we've put in. So the iterator would be equal to the domain name server lookup.end, and we'd print out this error message. Okay, so that's how we check whether it's found or not. All right, so that's what would come out of the output. Okay, so iterating over a standard map. And we put some values into a binary search tree, this map. To get used to writing code with this, we're going to do a breakout exercise where you use iterators in a for loop to print out all the nodes in the map. Okay, so you're going to need iterators, you're going to need a for loop, and we're going to go off to the online IDE and have you type that in. Okay, so Abid, if you can open up the breakout rooms, that'd be great. And I see the question, is it operator overloaded? Yeah, so that arrow operator is an operator. It is overloaded for iterators to just do the right thing. Same thing as like the dereference operator. Dereference is an operator. It's overloaded for iterators to do the right thing too. Increment, decrement, they overload all sorts of operators so that they behave like pointers. Okay, so I'll see you in the breakout rooms.
I don't think you are muted, but we can't hear you.
Can you hear me now?
Yeah.
Okay, sorry. I got an external mic that I think I got confused about. So let's see. We flip back to this. Okay, hopefully that went okay. If there are any questions, type them in the chat. But this is the typical solution to this. So we make an iterator that points to the beginning of the binary search tree, and as long as it's not equal to the end, we keep incrementing it. The type of this iterator is going to be a bit complicated. It's going to be the iterator to a map of a string and an integer. So we're just going to use auto because we can. The compiler again can figure it out because we immediately set it equal to this value. It can figure out what type it needs to be, so we can use our auto keyword to save some typing. The iterator to a map, once again, is pointing at a node in the binary search tree, which is a pair. So if we want to print out both the key and the value, we have to print out first and second. And yeah, that's what it'll look like. If we put this in our binary search tree, okay, so if we have these 3 lines of code inserting things into our binary search tree, what will this print out? What order will these come out in? Okay, so it's going to print out all of this data, everything that's in the binary search tree, but what order will it come out in? Just type it in the chat if you know. Yeah, it comes out in order, sorted value of increasing values. And that's right. So it comes out in order or sorted. Those both basically mean the same thing. It'll be sorted by key. Okay, so it's going to come out Apple first, Google second, uToronto third, because that's alphabetical order. So this is different than if we had inserted these things into a list, for example, where they would have come out in the order we put them into the list. A map is a binary search tree, so it's constantly sorting. They're going to come out in sorted order. Okay, so you basically know how to use a map now. You know how to insert things in the map. We haven't shown this, but if you want to erase things from a map, it's .erase, which you already know how to use as well. And if you want to look things up in the map, you use find. So you now know how to use a binary search tree without writing, much code at all. There are a few variations on these binary search trees inside of STL. So let's say that we're making a different data structure. Okay, so we're making an object called salary database, and we're going to have keys that are employee names, like John Smith, and we're going to have values which are the person's annual salary. And let's say John Smith is a common name, and we wind up with 2 people named John Smith. So we try to insert John Smith twice, and that's what we're doing here, is putting everybody in our salary database. And then down here, we're going to look for somebody named John Smith, and then we're going to print out the person's name and the person's salary. And for a regular map, we can't have duplicate keys. So the second insertion would not happen. It just would see that the key already exists, John Smith's already in there, and it would not put the second value in there. So for many things, that's what you want. But for the salary database, that's probably not what we want. We don't have a company that says, well, we can't hire you because we already have a person named John Smith. And we can't have 2 because it would break all our payroll software. So we don't want to say that. So we want to update it. Okay. So this code, it would always return this first John Smith if we did finds, because that's the only one who actually makes it into the binary search tree. Second insert's just not going to do anything. Okay. But there is a variation on map that can handle this. All we have to do is change the type that we ask for from map to multi-map. A multi-map is a binary search tree where we can have repeated keys. They all get stored instead of only storing the first one. So now if we do this, both of these entries, both these John Smiths, will go into our map or our binary search tree. So that's good. But if we do this find, if we say, find me the entry for John Smith, it's still unclear what should be returned. There are 2 different entries in this binary search tree that have key John Smith. So what will happen is STL will return just the first one it finds. So it's going to return essentially arbitrarily one of these 2 entries. Okay. So both of them are going to wind up getting the same salary. They're both in the database. They're both in the binary search tree. But whenever you do a find, you just get one returned essentially randomly. I see a question, what is a multi-map? So a multi-map is just a binary search tree where you can have repeated keys. If you have the same key, each time you insert, you get another node in the binary search tree. Whereas the regular map does not allow repeated keys. If it's already in there, it just does not put it in the second time. Okay. Where in the BST does it insert the duplicate? Basically, it's a sorted structure, so they'll all be together in the binary search tree. There'll be a sequence of nodes that have the same key, but you don't know exactly how they're ordered. because they're all have the same key, it doesn't matter. So it's an ordered structure. It will keep them in order, which means in this case, they'll all be together in the binary search tree when you do an in-order traversal. But other than that, you don't know, okay? Which is why the fact that we now just returned one key is problematic. There are more functions for maps and multi-maps. And the reason I'm telling you this is it's actually useful in milestone 1, and to point out that it's useful to go to references, and there'll be some at the end of this tutorial, where you can see what are all the functions available for these containers in STL. So there is a member function called equal range, and equal range gives the range of entries that match the key John Smith, okay? So instead of calling find, we call equal range. Still takes a key, takes John Smith, but this range is actually a pair of iterators. So basically the first is the starting iterator, the end is the ending iterator, and basically now there's a sequence of matches, and we can actually loop through and print out the key and value for each of those matches. So if we did that, we'd actually now get both of these coming up. This is a little detailed. The reason I'm telling you this is that this actually can be useful for a particular function in milestone 1. In order to use this, you go to c++reference.com or a similar website, and you kind of look up what are all the member functions for a multi-map. Okay, other containers. So very briefly, we talked about map. It's a binary search tree, which means find, insert, and erase are all pretty fast. Logarithmic in the number of things in the binary search tree. Multi-map is the same. Like I said, it's a binary search tree, but it allows duplicate keys, which can be useful sometimes. Unordered map, I'm going to very briefly outline, I think we'll do another session on it, but basically it is a hash table, which means it is even faster. It's order 1 access to find, insert, and erase, but it's not ordered. So it's not an appropriate data structure if you need your keys to be kept in order. If you just need fast lookups for things like strings, then a hash table is a great option. And then a set is very similar to a map. It just doesn't, it's when you don't have any values. You only care about keeping the keys sorted. I'm not going to talk about these other ones. There are more containers. They're not as commonly used, but you might wind up using a few of them in this course. So I'll just skip over that for now, but it's there for reference. Okay, so last slide. And again, I'll post some slides on hash tables because this probably isn't that understandable if you don't know hash tables. The map is a binary search tree. So it looks like this. And it's order log n to find an element by key because we start at the top and we go down some sequence, which is log n steps to get to where we need to be in the binary search tree. And it's fundamentally sorted, which sometimes is useful. An unordered map basically uses the same member functions, insert, find, erase. So the way you use it is essentially the same, but it's even faster. It's order 1 to find an element by key, but it's not sorted. And I'm not going to, if you haven't studied hash tables, you probably won't understand what this diagram means. But basically a hash table is a clever data structure where it can very quickly from a certain key, like a string or a big integer, it can figure out where to go get the data, even faster than a binary search tree because it doesn't have to do as many comparisons. It achieves order 1, insert, remove, and find. Okay, so that's it for all the slides I was going to go over today. Let me quickly bring up my VNC session, if it's still alive. It looks like it might have died. Let's see if it's still alive. There it is. Okay. Okay, so this code demo let's look at this top code. So this is code that is using a map. All right, so here's my main function. And I'm creating a map. This particular map uses both an integer key and an integer value, whereas the maps I was using in the tutorial were a string key and an integer value. So clearly you can use any key and value you want. And I'm going to make an object of this type and call it map0. Okay, so what do? I go from 0 to n, and n is a lot, it's a million. And I'm going to basically insert a whole bunch of random values. Okay, so my keys are going to be one integer and my values are going to be some other integer. And I'm just going to insert 1,000,000 of these pairs of integers into my binary search tree. Okay, now I'm going to go and do some searches. And I actually do 10 times as many searches. I do 10 million searches. I generate random keys, so random integers that I'm going to use to see is this in my binary search tree or not. And I'm going to search. So I search by calling the find member function with my key. And now my key is an integer. So again, keys can be anything. In this tutorial, they were mostly strings. Now I'm using an integer. And I'm checking here, did I find it? If the iterator that's returned, so remember, find returns an iterator, so a pointer to the element. If the iterator that's returned is the end, then I didn't find it. And maybe I printed an error message. But we haven't bothered because all we care about here is speed. Okay, so that's the first program. Second one is down here. It's exactly the same. The only thing that's changed is we've gone to an unordered map. And an unordered map is this data structure called a hash table, which is order 1 instead of order log n. But we do the same thing. We put the same 1,000,000 random integers into it, and then we do 10 million random finds. Okay, so we're going to compile this to check how fast is it. Is there value to using an unordered map if we don't need the data structure to be sorted? Okay, so let's do make clean. Get rid of any old data any old build that's lying around. Okay, so I'm testing speed. So what configuration should I use? Hopefully you guys have this. You can type it in the chat super fast. Okay, so it should be release, right? Always test speed with release. All right, and time command is my friend. So, and I've got 2 of these. So first I'm going to do map. So I'm going to time the map search. And so it did 10 million random queries. And again, the time, I can read it off of here, is a little less than 9/10 of a second. Or I can read it off of here. It says the same thing, 9/10 of a second. All right. Now let's do the other one. So that was with a map. Now I'm changing just one word in the program. My data structure is going from a binary search tree to a hash table, switching to an unordered map. Okay, if I time that, it's 0.28 seconds. So order log n to order 1 is not nearly as big a deal as order n squared to n or order n to order 1. So it's not as big a deal, but it still matters. This is about 3 times as fast because this second version that used a hash table is less than 0.3 seconds. So 0.284 seconds, if I include the operating system, 0.29. Factor of 3, which is worthwhile. Okay, so unordered map is a hash table. Map is a binary search tree. I can see there's a question on that. The advantage of a map is if you need sorting, because an unordered map's not sorted. If you don't need sorting, then an unordered map is going to be faster for large n. And it provides basically all the functionality of a map except the sorting. So you generally want to use unordered map if you don't need the sorting. I'll stay on the line. That's it for the tutorial today. There are a few more slides we didn't go over on the STL algorithms. They're on the website. The STL algorithms aren't as important, and you saw one of them, the STL find. So they're basically just templated functions that can be handy. And let's see, I think with that, we're pretty much done. I might have one last wrap-up slide. Okay, so the standard template library is really big. So we can't teach it all to you. We have just taught you some of the most important things, but it is very useful. It'll be very useful to you in this project. It'll be very useful in your career. And it's used heavily in C++ coding. Similar things exist for other languages like Java, like Python. So learning how this works also allows you to code more productively in those other languages because the syntax will be a little different, but the idea is the same. So how do you learn more about STL? So you go to a reference like c++.com. That's one of my favorite ones. And it has a breakdown of basically everything that's available. So maybe I'll just do that really quickly right now. So if I go to c++.com and I type in, maybe I'm interested in vector. So I type in vector and you'll see it shows me over here all the member functions of vector. Okay, so it gives me some information about vectors, and it tells me, let's say I want to look at, we were talking today about erase. So let's go look at erase. And it tells me how to use erase, gives me examples of how to use it, tells me what the complexity is. So it says linear, so order n. So it gives me a whole bunch of information. Also shows me what are all the member functions. Maybe there are some helpful ones here that I'd never thought of. So really useful. And if I wanted to go look at map, same idea. So now I see, what does map have? Here are all the member functions. And maybe I need to see, whoops, I clicked on find there, or erase. Maybe I need to see how the find function works. So it'll tell me exactly how to use the find function, and it'll give me sample code and so on. So STL is so big that I have not memorized it all. Abid, have you memorized the whole STL?
I still Google stuff today. Like
So
I never.
don't feel bad that you're Googling things and you're going to references like this. This is the way it's done. You understand enough of the basics to use it, and you know where to look for more information. And as you use it, you get gradually more familiar with it. But it'd be highly unusual for someone to have the whole thing memorized. So don't feel like you need to do that. Let's see. And that should be it for the, yeah, and ask us for help on Piazza. And that is the end of the tutorial. So I'm going to stop the recording now. Sure. Okay, and I see a couple questions. So I'll stay on the line and answer these questions. But obviously feel free to log off if you want to go grab lunch. In the standard vector int iterator, what is the second colon used for? What is it scoping to? Okay, so that's a good question. So let me go find a little example of that. I think I have to go back to my other slides. So, well, maybe I'll just write this. The second scope operator, so the question is basically when you have something like this, standard colon vector of int colon iterator, what is this second scoping operator doing? Basically, inside this class, vector, there's a subclass defined called iterator. So it's just how the standard library chose to organize the names. Everything in the standard library starts in what's called a namespace called std. And then the iterators, because they really go with a certain kind of container, they're actually defined inside that class. So it's like an embedded class. Inside vector of int, look for the iterator that goes with it. Let's see. And then I saw there was a question. Yeah, I see the question about slides for hash tables. I will find them and post them for those who want to know about hash tables. It is a good idea to know about hash tables, to be honest. Like, you not knowing what a hash table is, you don't, if you want to write software, you don't want to go through your career not knowing what a hash table is. This would be a very common kind of thing that could come up in an interview, and you'd want to be in your career.
The most common question I was asked in interviews last month was, what is the difference between a hash table and a binary tree, and how do each work in the background?
Yeah, so normally 244 teaches hash tables, so other courses will assume that you know it. So I will post these slides, and I really recommend you go through them. You might be able to go through the course without going through them and not really understanding the details of a hash table, but it's kind of a pretty significant gap in knowledge that it would be good for you to fill. And it's not that hard, right? The notion of a hash table, once you see it, is not incredibly difficult. Let's see. I'm just trying to go through the questions in order. Okay, looking up multiple values in multi-map. So let's see. Yeah, this one. Okay, so I think I'm on the right slide. Let me erase this because this was answering a different question. Is there a question on this slide? Because I see it looks like there was one. Oh, sorry, not this one. Okay, so you tell me whether to go forward or backwards. No, okay, yeah, you're right. I'm on the wrong one. It's this one. Sorry. I think that's the slide. Let's see, there's a question. Is there a case where the constant for an unordered map is so large that using a map would be better? It's unusual. To be honest, I can't really think of cases where a map is faster than unordered map, because an unordered map becomes faster at relatively low n. Because not only is it got order one access, the constant is not that high either. Abid, can you think of a case where, I mean, it's hard to give absolutes, but even for relatively small n, an unordered map is likely to be faster than a map.
Yeah, the average case is always an ordered map of 1. If you know how the hash maps are implemented, conflicts might
There won't be
might
many
make
conflicts the way they.
yeah, there won't. It's rare, but it might. The worst case is off n,
okay.
but this is very rare.
Yeah, maps kind of are always log n. Hash tables average order 1. So one particular access might be a bit slower, but the average is order 1. So I guess if you wanted really deterministic access, then maybe a map, like you need to guarantee every single access is always fast. There can't ever be one that's a bit slower. Then maybe map has an advantage in that. But yeah, unordered map is almost always faster. Again, if you don't need sorting, because it doesn't provide sorting. Because not only is it order 1 instead of order log n, this is now more detailed, but the way that it accesses memory, and you're going to find in 243 and later courses that how you access memory actually matters. The way a hash table accesses memory tends to be more friendly to a CPU than the way a binary search tree map accesses memory. A binary search tree has a lot of pointers inside of it that it's following, and following pointers, because memory is very slow compared to a CPU, following pointers tends to be harder to make fast for the CPU. All of that means that this is a case where, yeah, you don't need to get to really big n before an unordered map becomes faster. It's usually faster even for small n. Okay, so now I think I'm finally getting close to it. This one. Okay, this one. Yeah, the code here looks pretty funky. So I'm giving it to you for an example because, as I said, it's useful in milestone 1 for one particular function. This is where, to write this, I went to c++.com to look up what is the exact syntax. Give me an example. And I think this is the one. Is that it? Or is it the next one? I think that's it. Have I got the right slide now?
There is an error in the cout statement, by the way. You missed the all stream operator after first.
Let's see. Did I miss one?
But I fixed it.
Oh, you're right. Okay, Avid, I owe you a bonus mark. That's good. You caught that. All right, you're right. I'm missing some O-stream operators. I'll fix those after. Yeah, it's possible for an unordered multi-map to exist. So it's the same idea. You can put in duplicate keys, so there's no problem with that. So Chris, what is your question on this slide? Is it just, it's a bit funky. What it basically says is when you call this equal range member function with this key, I'm going to get back all of the entries, so key value pairs that match that key. Okay, so how is the standard library going to give that to me? Well, basically all those entries are going to be in my binary search tree, essentially in sequence, like if that makes sense. So it would be, let's see if I can write the sequence of a binary search tree or not. It would be something like this. So this might be John Smith, this might be John Smith, this might be John Smith, and this might be Michelle Smith. Okay, so a different person. So it'll return a pair of iterators. This will be the first iterator points at the first node that matches, and the second iterator points at the first node that doesn't match. So this is basically range.first, and this is going to be range.second. So now you can basically say, I'm going to start an iterator at range.first, and I'm going to keep going as long as I'm not at range.second. And every time I iterate, I'll point at the next thing. So I will walk through the part of the tree that has all of these matches. And at each match, I can print out what's at that node. I can print out the key and the value. Does that make sense? So yeah, it's returning a pair of iterators that you can use to walk through the part of the tree that has the matches. Excellent. So, and you got to walk through. This one has like, pairs of pairs and so on. So you really do have to walk through the code fairly carefully to understand what the heck's going on. I have to walk through it very carefully too, or I confuse myself. Let's see. Is it impossible for an unordered multimap? Yeah, so it's not impossible. There is an unordered multimap. In fact, I think I can just go and look at it right now. Let's go click on this. I can find my cursor. Huh, that's odd.
Or you can do an unordered map with where the key is where the value is a vector.
Okay, well, now I can do it. So let me do a Control plus. Okay, so let's do an unordered, should be an unordered multimap. See if I get the syntax right. Yeah, so there it is. So it's an unordered multimap. It's not impossible to exist because it's the same notion as a binary search tree. You can put the same key in multiple times. They'll all be sorted to be essentially a contiguous part of the tree. You haven't learned what a hash table is yet, but a hash table is a data structure where, yeah, actually I can't explain it in just a few words, but it basically is a data structure that can very quickly map from key to value. And there's nothing that says you can't have repeated keys either if you code it properly. The basic data structure can handle it. You just insert all of them, and you have to make sure that you check that are there any more keys that match before you return the value from equal range. So it's not that different. So we're just wondering how the hash function could distinguish between distinct values from the same key. They're all stored. So it's basically the same way that a multimap works. A multimap, every time you insert with some key and some value, it makes a new node in the binary search tree, even if the key already exists. So it puts it in the right spot. They'll all be kind of grouped in the same part of the binary search tree, but there'll be a new node every single time, no matter how many times you insert a certain key. And if those different nodes have different values, that's fine. They all exist. An unordered map is the same. Every time you call insert, it goes and checks where should I put this according to the hash table rules. And if it's an unordered multimap, it doesn't matter if there's already stuff there. It'll basically add essentially another node. The way that node is stored is a little different than the way it's stored in a binary search tree, but it's the same idea. It creates another node that has a key and a value. So the value may be different than any of the nodes that are already there, and it sticks it in there. So it now knows that that key was inserted maybe 6 times with the following 6 values. It stores them all. And if you need to loop, let's see, if you need to look up an entry, you need to loop through the returned range to find the actual entry. Yeah, so for a multi-map, when you have to go look through its member functions, because this is now you're getting into where I haven't memorized everything, but it's the same. It's equal range. So unordered multi-map, if you just call find, and there are multiple keys, you're using an unordered multi-map, you'll get one of the key value pairs arbitrarily selected. Okay, so the same key, if you inserted John Smith 7 times and you call find, you will get one of those nodes, but you don't know which. If you call equal range, then it's just like what I showed you. You're going to get a couple of iterators that allow you to walk through a list of, well, it's not stored as a list, but basically go through a sequence of 7 John Smiths. And you can print out the key, which will always be John Smith, and the value, which could be different for every single one. So it's the same idea. You call the same function equal range. How it's implemented under the hood is a bit different because it's a hash table, but you as a person calling it don't really care. That's actually the nice thing about STL. It keeps using the same member functions for different data structures. So you can actually write the code and not really care too much about what is the underlying data structure, except you've just thought about this would be a good one for efficiency. And then the code you write is basically the same. Let's see. Okay, how important would data structures and algorithms be if you're taking AI fundamentals and intro to machine learning, since it isn't listed as a prerequisite to any of them? It's not strictly necessary for AI. Data structures and algorithms is pretty important software engineering. And I would say that because you guys haven't gotten to hash tables, that means that there's even more value to taking it because you haven't gotten as far in data structures as usually we do. So it's pretty important for software engineering.
I think personally, software, like, you cannot be a software engineer if you don't take algorithms and data structure courses.
Yeah,
it's that important.
Pretty fundamental. Like basically, knowing when to choose the right data structure and the right algorithm is part of what differentiates a computer engineer from a typical person, there are always exceptions, but a typical person who went through a whole bunch of Khan Academy things and learned how to program, various web clients and so on. Usually those online resources don't emphasize efficient coding and teach that underlying, that level of underlying detail. And you go work for places like Google and Microsoft and Intel and so on, they need efficient code. They're doing this stuff at scale. They're not just trying to hook together a bunch of web pages. So data structure is very important to be a successful software engineer. AI moves a lot of data. So if you only use AI libraries, then you can get by saying, I don't quite know what they're doing, but it's a bit limiting. If you ever have to code something in an AI library, code some pre-processing code, you want to know how to do that efficiently. So I'd say it's pretty important. And it seems like Abbott agrees.
Yeah.
This course is actually designed to sort of go with our data structures and algorithm course, because the data structures and algorithm course at U of T doesn't do any coding. That's part of why in this course we make sure that you actually code some algorithms and some choice of data structures. So that it kind of complements the more theoretical but wide-ranging treatment that you'll get in that course.
I'm not a professor, so thank you, Professor.
Abbott has almost got his PhD. You're lucky to have him
so.
in
Fingers
the course.
crossed.
This is going to be the last time. He's going to graduate in a few months. So. And he knows data structures and algorithms, and there was a feeding frenzy to hire him. So, so he's a few months away from graduation and could not put off taking a job. So, because there were companies chasing him. So knowing these things is quite helpful.
Thanks a lot.
Perhaps one day he will come back and be a professor. So
probably we'll see.
After he's gone to industry and made his mark, maybe he will come back and one day teach 297. So. Okay, so if there are no more questions, I think we're going to sign off and end the recording. Thanks, everybody.
Yeah, I think that's it.
Okay, thanks, Abbott. I'm going to sign off too.
No problem.
Bye-bye.
You, sure. See you.